All right, this is Mr. Baker, and we're looking at the geometry review for the Tennessee end of course test, Integrated 2. This first box on your worksheet has all the formulas on it: area of a circle, volume of something flat, volume of something pointy, circumference of a circle, area of a triangle, as well as the concept of surface area described here. We didn't really focus much on surface area, but we could see those. So number 7 is definitely a surface area problem. We'll probably see that pop up somewhere. But let's just go ahead and get into it. This first problem is talking about BE being parallel to CD. Well, when we have a triangle and that triangle is cut by a line parallel to one of its sides, it's going to give us some stuff. First of all, it gives us similar triangles, and we could do this as a similar triangles problem. That would be really useful if I needed to find BE or CD. But I'm looking for AB, and everything I have is going to be along these two sides. So the advantage of that is that I can just use the fact that parallel lines, when they cut through two different lines, are going to give us proportional pieces. So parallel lines create proportional parts. That's a hard one to say, a lot of P's there. Proportional means that we're going to have two fractions that are equal to each other. So let's label a few of these lengths. Let's start with what they tell us. AB is 8. Now it tells me AC is 10. That would be a little more useful if I could get just BC, but that's just a matter of subtraction. 10 minus 8, that's going to be 2. BC is just going to have a length of 2. So what else do we have? We've got ED is 3, and we're looking down here. It tells us or asks us what the length of AE is. So that's the one we're looking for. We'll make that X. So what does proportional parts mean? That means we can make fractions out of them. 8 over 2 equals X over 3. There's other ways we could put that together, but it was this big piece over this small piece, this big piece over this small piece, is the way I put it together. And now we can solve for X. When you've got fraction equals a fraction, probably the most standard thing to do is cross multiply. That's going to give us 8 times 3 equals 2 times X. Remember, it's the bottom of a fraction times the top of the other side. So 24 equals 2X. Get X by itself. Just divide both sides by 2. X equals 12. So that AE we were looking for has a length of 12. Similar triangle problems typically, or any similar figures, usually are going to be setting up proportions so we can cross multiply them. All right, in order to find the density of a rock, density is a concept that you may get in science class. We don't really need to know about density. Specifically, Michael needs to find the volume of the rock. But rocks aren't always a nice, neat shape. They're not usually a rectangular prism or a sphere. So it's probably got a weird, lumpy shape to it. So Michael does Archimedes' principle here. You don't have to know that either, but he puts it into a cylinder, a container shaped like a cylinder. And so cylinder, there we go. The base has a diameter of 20 centimeters. The height is 12 centimeters. But we don't need to know the volume of that whole thing. Michael puts water in the cylinder until the water has a height of 6 centimeters. So let's just fill it up some so we get that. Now let's figure out what volume that water is. It's probably a good way to start. Not the only way to do the problem, but it's a good way to start. So the volume of a cylinder, it's flat on top and bottom, so that's going to be area of the base times the height. That was our volume of anything flat on the top and bottom. But area of the base, what shape is my base? Well, when it's a cylinder, we've got a circle for our base. How do we find the area of a circle? Well, that's pi r squared. So area of the base times the height, that's pi r squared, then times the height. So we should be able to figure that out. Now, we don't have the radius of the circle. We have all the way across. That's the diameter. How do we get from a diameter to a radius, just have to take half of it. So our radius for our volume of water is going to be that pi times the radius is 10, pi times 10 squared, and then times our height. Now, is our height 12? Now, the height's not going to be 12 because my water doesn't go all the way to the top. It only goes that 6 inches. So that right there is what I need to use as my height. The cylinder will hold more, but all we've got is 6 inches worth of water, and now I can multiply all that together. Pi times 10 squared times 6, that's going to be 600 pi. You're probably best off leaving that pi as a pi symbol, just like treating it as a variable like it was an x, until the very end of the problem. So that's how much water we have. But that's not the whole problem. The next thing it asks us, or the next thing we need to do, we're trying to find the volume of this rock, so we're going to put the rock in the water. So there's the rock. Let's put him in the water. And that changes our water's height. Now it's 9 centimeters instead of 6 centimeters. Well, we should be able to find the volume of that. The new volume of the water is just pi times 10 squared times our new height of water, which is 9 instead of 6. Well, that's going to be 900 pi. So how does that help me figure out the volume of the rock? Well, since when we put him in, it changed an amount, all we should have to do is subtract these two volumes, because the only thing we added to this, we didn't add more water, we just added the rock. So whatever it changed by should be the volume of the rock, will be the volume of the rock. So we just have to subtract. 900 pi minus 600 pi, that's going to be 300 pi. That's going to be the volume of the rock. Put that in the calculator because it does ask us to round to the nearest cubic centimeter. I know I worked over some of the directions there, but to the nearest cubic centimeter, we do want to put that in the calculator, 942 cubic centimeters, and that's going to be the rock's volume. Now, this problem could have been done, we could have just subtracted and done the volume just once. The 6 centimeters subtracted from the 9 centimeters we get after adding the rock, then it would have been pi times 10 squared times 3. That would have given us 300 instead. Still some subtraction involved. It doesn't really matter if you find the volumes and subtract, or subtract to get the height. All right, that theta right there suggests that this is definitely going to be involving an angle, and it is. I see cosine theta there. This is definitely a trig problem. Let's read the whole thing, though. Let theta represent the smaller of two acute angles in a right triangle, such that cosine of theta equals 0.75. The longer leg of the right triangle measures 12 feet. What is the length of the hypotenuse? So I don't have a picture here. I need a picture. Let's get a picture. Draw a triangle. Any right triangle will do. It does say it has a longer leg, so make sure you got one short leg, one long leg, and then of course hypotenuse is the longest of all. And it's talking about the theta being the smaller of the two angles. Well, here's the smaller angle, so let's make that theta. And then we can label some other stuff. The longer leg is 12 feet. I'm looking for the hypotenuse there. And we don't care about this other side. Well, whenever we're working with angles and side lengths, that's going to be a trig problem. So we want to think SOHCAHTOA. What sides am I working with? Well, start any SOHCAHTOA problem by labeling your opposite, adjacent, and hypotenuse. Hypotenuse, opposite, adjacent, just like that. So what do we got? We know the adjacent. We're looking for the hypotenuse. Adjacent and hypotenuse, that's going to be the ka part, A and H. So that's going to be a cosine problem. Another nice indication of that is it tells us the cosine. It could have told me something else We've worked with problems where we switch from cosine to sine or cosine to tangent if we need to. But this one was nice enough to give us a cosine. So if we know we're working with a cosine problem, we should set up that fraction. Ca means cosine of theta is opposite over hypotenuse. So plug in what we know. We don't know theta. We do know the adjacent. We know the hypotenuse is x. But the other thing we know is what that cosine is equal to. So we don't actually have to plug in an angle. We're just going to go ahead and say cosine of theta is 0.75. So we replace the cosine theta with 0.75. So now that equals 12 over x. What do I do? Well, I want to get x by itself. Most of the time we talked about making that left side into a fraction so we can cross multiply. So that's going to give me 0.75 times x equals 12. Now I just need to finish getting x by itself. That's being multiplied by 0.75, so I have to divide by 0.75 to finish getting it by itself. X is going to equal, calculator might be involved there, it's going to be 16. So x equals 16. Now, really not a lot of other ways to do this problem. You could do it where you find the angle, but it still would have been a cosine problem, so I don't think that would have helped. But if you want to do the inverse cosine and find the angle, you could do it that way. It might feel a little more familiar that way, actually plugging in an angle. All right, this one's just a little bit weird. It really is just an area problem, but it's kind of related to a surface area problem. And the picture here shows us a lot. The tube inside a roll of wrapping paper has a diameter of 3 inches and a length of 30 inches. It is made using a rectangular piece of cardboard as shown. So we just take this rectangle and roll it up to make that tube for the wrapping paper. What is the approximate area in square inches of the rectangular piece of cardboard? So it doesn't quite tell us where to round that, but we can work with that. We're just looking at the area of this piece of cardboard. We need the area of a rectangle. All I need for that is length times width. The length is easy enough to spot. It's the same as the length of the roll of wrapping paper. It's going to be 30 inches. But the width, how are we going to get that width? The width really, if you track it back, is going to be the same as the circumference of this circle, and that is a circle. Well, when we unroll the piece of cardboard, we unroll that circle as well. So what was a circle is now straight, and what was a circumference is now the width of that rectangle. And that's much easier to work with because I have a number. I've got the diameter for the circle. That'll help me find the circumference, and then I can turn that into my width. So how do you find circumference of a circle? That's pi times 2r, and 2 times r is just your diameter. So pi times the diameter, pi times 3 is 3 pi. That's my width. It's not a circle anymore, but it came from a circle. That's why we've got a pi there. Well, now just length times width, 30 times 3 pi. That's going to give me 90 pi. I can put that in my calculator and get 282.7 square inches. That's going to be your approximate area, maybe 283, depending on where the rounding needs to be. Now, it is just an area. It's not a volume, so we definitely want square inches. Now, what if it didn't ask for the approximate area? Because that is the approximate area, but what if it doesn't say approximate? What if it asks for the exact area? Well, an exact area, exact measures from circles tend to have pi's in them, so the exact area would have been 90 pi. Number 5, a ramp is built onto a platform as shown. To the nearest degree, what is the angle between the ramp and the ground? We've got some numbers here for lengths. Anytime we get sides and angles mixed together, that's going to be a trig problem. Bring on the SOHCAHTOA. So what sides do we have? Let's label everything. Always the first step in a SOHCAHTOA problem. Opposite, adjacent, and hypotenuse. I usually start with a hypotenuse, opposite and adjacent like that. Now this time we're not looking for a side. We know two sides. So which two sides do we know? We know the opposite. We know the hypotenuse. We don't care about the adjacent, but opposite and hypotenuse, opposite and hypotenuse. What uses opposite and hypotenuse? Well, that's the SOH, S-O-H, sine of theta equals opposite over hypotenuse. So let's plug in what we know. We don't know theta. That's an angle. That's what we're looking for. So sine of x specifically is what we're looking for, is opposite over hypotenuse, 7 over 19. How do I make the sine go away so I can find an angle? Anytime you're trying to find an angle in a trig problem, that's going to be an inverse trig problem. Since this is sine, we're going to do the inverse sine. That's how we make sine go away. If I take the inverse sine of one side, I have to take the inverse sine of the other side. That's what's actually going to go in my calculator and give me my answer. Inverse sine and sine cancel out, and x is going to equal whatever the inverse sine of 7/19 is. By the way, make sure your calculator is in degree mode. If it's not in degree mode, it's going to give you a completely wrong number, and you may not know. Although it is kind of an indication, it'll probably come out somewhere less than 3, and this probably isn't a 1 degree angle or something. So when we put that on our calculator, that's going to give us 22 degrees approximately. It says to the nearest degree. That means the nearest whole number, so that's where our rounding is going to be. Again, if it asks for an exact, though, it doesn't. It says to the nearest degree. But that's inverse sine of 7/19, that's your exact answer or your symbolic answer. And a lot of the times on multiple choice problems, the ACT likes to do that too. They'll use that symbolic answer. Number 6, which of these could not be the lengths of the 3 sides of a right triangle? Select all that apply. So basically this is 5 little true-false questions or 5 yes or no questions. And the way we decide if it's yes or no is we put them into, well, the formula we have for working with sides of a right triangle is the Pythagorean theorem. A squared plus b squared equals c squared. Make sure your c is the biggest side. So in this first one, c has to be 10. 8 and 6 are going to be your a and b. So 6 squared plus 8 squared equals 10 squared. Does that work? Sure does. That's a yes. That's one of my answers, right? Wrong. Why? It says which could not be the lengths of a right triangle. Sometimes the directions are going to be written deliberately in a weird way. So even though we got a yes, it's not one of my answers. So be careful for that. How about B? Let's try that one. 1 squared plus square root of 2 squared equals square root of 3 squared. What happens when you square a square root? You just get the numbers inside. So that's really 1 plus 2 equals 3. Does 1 plus 2 equal 3? Yeah, it does. So that's a yes. But I'm not looking for yeses. I'm looking for no's. So B is out. Always read your directions carefully. How about C? 3.3 squared plus 4.4 squared equals 5.5 squared. Honestly, we can take a shortcut if you recognize that that's just a 3, 4, 5 right triangle where each one's been multiplied by 1.1. Sometimes those can be hidden on us. It can be a little bit dangerous to trust that. It's got to be just multiplying, nothing else. You can't take a 3, 4, 5 and add 1 to them or square them and make it 9, 16, and 25, because that doesn't actually work, because you have to square them when you plug them in. So if that all sounded confusing, just use your calculator and check these out. 3.3 squared plus 4.4 squared. Does that equal 5.5 squared? It does. So that's a yes. So is that an answer I want? No. How about this one? 5 squared plus 14 squared equals 15 squared. Do they? That one actually doesn't. They come close, but they're not equal. So that's a no, but I want no's, so that's actually one of my answers. Now, remember when I said 3, 4, 5 is one of those patterns we look for, but only if they're multiplied. These aren't just 3, 4, and 5. They're square root of 3, square root of 4, and square root of 5. And they haven't been multiplied by something. Some other operation's been done, so it doesn't actually work. Square root of 3 squared is just 3. Square root of 4 squared is just 4. Square root of 5 squared is just 5. But 3 plus 4 does not equal 5. That's a no, so that's an answer I want. Hardest part about that problem is the fact that the directions just seem kind of backwards from the way we work it. And this brings us to number 7, the surface area problem. Well, surface area is just looking for us to add up all the areas of the surfaces, the flat surfaces. And the 3D picture here, you've got perspective going on. So if it looks like it might be a right angle, it probably is, which means that the shape we've got on the bottom definitely is some sort of a rectangle. As a matter of fact, that's going to be a square because the length and the width are both 10. 10 times 10, length times width to get our area, is going to be 100. What other shapes do we have here? Well, on that left side, that slanted side is going to be a rectangle, which is 10 by 12. 10 times 12 is going to give us 120. And as it turns out, that right slanted side is also a 10 by 20 rectangle, so we got 2 of those. So far we've got a square with an area of 100, 2 rectangles with an area of 120. What other shapes is this made up of? Well, it is a triangular prism. So we've got a triangle. We got one on the back. So how do you find the area of a triangle? Well, area of a triangle, 1/2 base times height. That's one. We haven't used it quite as much as you might expect, but it's definitely one that you should know. It's definitely one that you learned when you were in elementary school, starting to multiply with fractions. So it's one that's been around for a while. Maybe you learned it as base times height divided by 2. That works fine. So what's my base? My base is 10. It's always the side that the height is measured to. It's going to be at a right angle to the height. And since this side was 10, this back was also going to be 10. What's the height? 10.9. So 1/2 times 10 times 10.9, that's going to give us 54.5. So that's our triangle. How many of those triangles do we have? Well, we've got that triangle on the back. We also have a triangle on the front, exact same sizes, so it's going to have the exact same area. Finally, we just need to add these up. We add that up, it's going to be 449. And that's just a little addition. 449 what's though? These are all measured in inches, so that's going to be in square inches. Any sort of area, even though it's 3D, volume is cubic inches, but we're not filling it up. We're finding the area of all the shapes it's built out of. So 449 square inches. And that's it for our geometry. There's other things that we covered in geometry. We definitely covered Pythagorean theorem in more depth than just checking for right triangles. We did all sorts of different trig problems. These were really just there to trigger your memory as we head into the end of course test. So hopefully it's got you thinking about your geometry and ready to go.